Good morning. It's the 10th, and I thought I'd take a few moments to talk about the essay final exam. Remember, there'll be no multiple choice having to do with Chapter 10 or Chapter 15 because everyone did the homework for Chapter 15 so well that I didn't feel like we needed to turn right around and do an exam on it. So we'll let that go. The final exam then will be one of the 3 questions that I sent you last week. Now, let me say that you'll have 2 hours on Blackboard to do this essay. Well, it'd be tempting to have the text in front of you, but I wouldn't do it. I'm not saying don't do it or you can't do it, but I wouldn't do it. And that's only because fishing around in the textbook and fumbling around looking for something or other there will take up more time than you will imagine, and 2 hours will be over before you're finished. But what you might want to do, and I encourage you to do, and it's okay to do, is get a 5x7 note card and write down some points. Use both sides, of course. Write down some points that might be of interest to you in answering these 3 questions. Things that you want to be sure to remember, and things that you think you might not remember, so you better write them down as reminders. So use a 5x7 card and stay away from your text. I tell you the text you'll not finish. All right, so when I finish with the video, I already put the test out there. When I finish the video, I'll turn on the final exam, and you can take it any time between sometime this morning, it's about 7:30 right now, till midnight on Friday of this week. And then sometime over the weekend or on Monday of next week, I'll go into Blackboard and I'll grade them, and then I'll send you by email, or maybe I'll post them on Blackboard, what your scores are. But anyway, you'll know your the final exam by the end of the day on Monday, and I'll send you also your grade, so that you'll know how I'm going to post your grade for the course on the next day, Tuesday. The grades are due by a week from today by 5 o'clock. Okay, so the next thing is question number 1 will not be on the exam. So you can remove your consideration for question 1. It will not be on the exam. I can just tell you it will not be. One of the question that will be on the exam will be either question 2 or question 3 on the study guide that I sent you last week. All right, let's look at for a moment. Make a few notes about question 2. I think one thing for both of them, both questions, I've made references to chapters in the text. I think it would be a good idea to look at the text for these chapters. Question 2, chapter 6 and 7, and question 3, chapter 8, and those items of the various items in problem 18, and chapter 9. Take a look at the learning objectives. If you can answer the questions or understand the meaning, are able to describe or write some response to the learning objectives, then you'll be all right on answering these either one of these 2 questions. For example, the first in learning objective, chapter 6, explain the purpose of inferential statistics in terms of generalizing from a sample to a population. Well, you're probably pretty familiar with that. The homework seems to suggest that you are. But you would want to keep in mind the pathway that we have put up on the board in one of the previous videos, where the idea is to go from the population directly to the parameter. But the population being so large, maybe 1 million or so, if say the city of San Antonio, the cost of going directly to the parameter, figuring from the population parameter, is prohibitive, both in time and money and personnel. So we draw down a sample, and because we have used a random sample, and the number of those random sampling procedures are in Chapter 6, then we have a sample that is unbiased, a term that's from the first part of Chapter 7. Unbiased means that it is representative of the population. In other words, the sample demographic features are very similar to the demographic features of the population, such that if we ask questions of the sample, we are in effect asking questions of the population. So as we bring it down, there's a random sampling, and that makes it representative and unbiased. And we come down to the sample, and we make sure that we have a sample, let's say, of 100 or more. That follows the central limit theorem in Chapter 6. And then as we do our calculations on the sample, we get a statistic. The statistic is our estimate of what we would have found, is our estimate of the parameter, what we would have found had we gone directly from the population to the parameter. Now, having found the statistic, then we can say, because our central limit theorem says that the larger the sample size, the closer the approximation of the population. And one of the issues of the first part of Chapter 7 is efficiency. The larger the sample size, the more efficient is the estimate of the population parameter. That whole sequence here is inferential statistics. We can't go from population to parameter, so we draw down a sample, analyze the sample, get a statistic, use the statistic to estimate the population, and because we are random, unbiased, and representative with a sample of sufficient size, we have efficiency, a good estimate of the parameter, and so that we can infer, had we gone from population to parameter, we would have found basically what we found going from the sample to the statistic. Now, so those are some good terms to keep in mind: efficiency, representative, unbiased, parameters, statistics. When you're writing about sample and population, the differences between all of those as you're writing a response to question 2. The other thing to keep in mind that kind of leads us into Chapter 7 is we are a point estimate. If we draw down one sample, that's one point estimate in time. Now we're comfortable with it because it's random, it's representative, it's unbiased, it's 100 or more, it's efficient. We think it's a reasonably good estimate of the parameter, but we know it's just one sample. We know that if we were to draw down 100 samples of the same size, there would be some variation. Let's say we're talking about average age. We draw down a sample, we get an average age of those 100 people. Say it's a sample of 100. But because all of the rest of the factors being what they are, we think that's a good estimate of the parameter. But we realize if we were to draw down 100 samples of the same size, there'd be a range in those means. The next 100 people might vary a little bit in their average age. The next sample, a little different still. So we recognize that there's variation in the mean of those 100 samples just because the composition of each sample is a little bit different. Now they're not going to vary by too much, but they'll vary nonetheless. So it takes us into Chapter 7 where we get a confidence interval. In other words, we get an interval in which we have confidence that somewhere in that interval is the true parameter. Now we believe, because we've done a representative sample, unbiased, sample size is sufficient that makes the estimate efficient, that our original mean is a good mean, but we do recognize the variability. So we do the confidence interval. Now, the confidence interval is constructed, if you'll remember, from 95% probability when we have, if you remember from the standard deviations, you have 68% of the of any distribution between plus or minus 1 standard deviations and then plus or minus 2 standard deviations, 95%, and plus or minus 3 standard deviations, 99%. That's from the distribution of the sample. If we up here in the population, we have the population distribution, which takes a normal curve. And think back on chapter 5 for a moment on the normalcy of curves and how those are shaped and the dynamic of that. If we have something over 100 in the empirical sample, the one of our single point sample, then it'll take a normalcy as well. And if we have 100 samples of the same size, then we have in the intermediate area a sampling distribution of 100 samples, and so that the largest sample is on the right hand side in that tail, and the smallest sample is on the left hand side in that tail. And then you have the heap of samples like you would, remember these are bar graphs, and it's a dot to dot to create that normal curve. And then you have the mean of means, the grand mean, which if you look at the second theorem in chapter 6 is considered to be the really true estimate of what the population mean is in the parameter. So in the sampling distribution, we have standard errors. They are the same vertical distinguishing characteristics in that distribution of that normal shape as are the standard deviations in the empirical. But we call them standard errors in the sampling distribution to simply distinguish them from standard deviation. Somebody says standard deviation, you're talking about the empirical sample. Somebody says standard error, you're talking about the sampling distribution. Way to keep ourselves oriented in all of these various shapes that are in front of us as we do statistics. So 95 out of 100, then, if the plus or minus 2 standard deviations is 95% of the distribution, both in the standard deviation in the empirical and the standard errors in the sampling distribution, then that's for the most part where those vertical bars will be. Those standard errors make up the ends of the interval, 95 out of 100. 95% of the distribution, or 95% of those means, sampling means, will be within those vertical standard errors. And if you remember, the z-score is 1.96, so that anything outside that is considered to be dissimilar and not likely to be the parameter, although it's a chance that it's there. Those means that are within the standard errors that comprise the interval are considered to be similar, just by definition, by consensus in statistics. So we use the confidence interval to give us a little more confidence that you remember from calculating the confidence intervals, which you did well, then you get a plus or minus, say the mean is 62, and then after the confidence interval it's plus or minus 3. So it might range between 59 and 65, if you remember how to do that. So those are basically the terms I think that are most important for and processes and concepts for answering question 2. Now let's think about question 3. These are for the most part chapters 8 and 9. Here, whereas in chapter 7 we didn't have the parameter. We were trying to estimate the parameter in chapter 6 and 7. We don't know what the parameter is, so we're trying to estimate it. And we're considering everything that's inside the standard errors, plus or minus 2 or 95%, are similar. So that somewhere in there is the true estimate of the parameter. In chapter 8, we don't know what the parameter is. In chapter 8, In chapter 8, we know what the parameter is. And what we're trying to do in chapter 8 is something very different than what we were doing in chapter 7. Here we're doing something, if you go back and you look at the opening part of chapter chapter 8, they have a couple of illustrations here about how to consider this. This is a situation, let's say, where, like using your illustration number 1 on page 179, where you might be wanting to do some research or practice related to elder crime in a neighborhood. And you're convinced from having spoken with the elders and from the literature and your own gut instinct that the crime rate in the among the elders in your neighborhood of interest is much higher than it is in the city. And so what you want to do is you want to provide some evidence to a funding agency, say it's the county judge, that you want to provide some evidence to the county judge, say for $250,000, to develop a crime education program for elders in your neighborhood. But in order to get that evidence, you have to show statistically significantly that the difference between the rate of crime in the neighborhood is different than the rate of crime in the city, such that it is much higher, let's say, statistically significantly so, than in the city. So here we know what the finding is, the statistic is in our sample, which is of elders, and we know what the population parameter is in the city, something we may have gotten from the police department or from some area aging organization or something where we have those statistics that are parameters of the larger population. So we have two hypotheses here, both in chapter 8 and 9. One, the null hypothesis is that the difference, any difference that we see between our finding in the neighborhood, in this using this illustration, and the city, is only trivial. It's not statistically significant. Our research or practice hypothesis is that it is statistically significant. That it is the crime rate for elders is higher. And so your argument as you go through this is to build the evidence to take to the judge that will show the judge that the $250,000 is warranted for the crime prevention education program of the elderly in your neighborhood. Now, there are a couple of things you want to think about here, and that is that we have one-tailed and two-tailed tests. Remember, everything at this point we're in normal curves. And whereas before, in Chapter 7, we had two tails out there that were error tails. In other words, we didn't want to be out there. We figured if it landed out there, then we misestimated. We didn't make a good inference. We're hoping that the parameter is inside the standard errors that represent those intervals, the confidence interval. In Chapter 8, we want to be out in the tails. We want to be different. If we land in, say we're using 1.96 to bound our rejection zone, let's say, of the null hypothesis, then if we have a z-score smaller than 1.96, then we're inside the area of similarity, which means that the null hypothesis is likely to be true, and any difference that we see is only trivial but not statistically significant. What we want in chapters 8 and 9 is to land in the tails in the dissimilar areas so that we can say that what we have as a finding in our sample is so dissimilar from the population parameter that we can judge that it is statistically significantly dissimilar. And you remember that they are rejection zones, the tails are, one way the text describes them, and that you have say a z statistic that is observed, that is the finding, or it could be a t statistic of your sampling calculation, and then so if you have a z observed from your calculation, then you compare that against the z critical from the table in the back of the text, and if your z observed or your t observed is larger than your T critical or your Z critical, then you may reject the null in favor of a research hypothesis. So that is basically the principle of Chapter 8. You know, you've got those 5 steps that you do, your assumptions, and which one of the distributions you're going to use, the Z or the T, and whether you're going to use a one-tailed or two-tailed, and then your calculations, and then the decision that you make whether or not to reject the null. I think for the most part, I think I've mentioned this in the video, for the most part you always want to do a one-tailed test. You will know from qualitative study of the neighborhood, you will know from talking to people in the neighborhood, your gut instinct, from your research that you've done using the illustration we just spoke of, that you're fairly convinced that the rate of crime among the elderly in the neighborhood is larger than up in the population. There's no reason to do a wishy-washy two-tail. You don't know whether it's lower or higher. There are some circumstances in social sciences where you might want to do a two-tail, but for the most part, you want to do a one-tailed test. You want to stick your chest out. You want to have confidence. You want to be able to demonstrate that you're right, that yes, indeed, in fact, the crime rate among the elderly in the neighborhood is higher than it is in the city. So do one-tailed tests. The principle's the same. You'd have a Z-score, and you'd want to land in the rejection zone in order to demonstrate that the null hypothesis is likely untrue. Basically, one tail. Now remember, you can be one tail in the positive. In this case, it would be a positive. If for some reason your research hypothesis, is that the value is supposed to be less than the null, then you'd be in the left-hand side in the negative tail. But the principles are the same. You remember in Appendix A, it's a symmetrical. Since the normal curve is symmetrical, Appendix A only gives you the positive values, but that's only because a -1 is the same Z-score as a +1 when you look at Appendix A. Okay, I think the other part is Chapter 9, and here what we're looking at is the differences between two subsets of a population. I think the illustration that's used there, that's an interesting one, and that's gun control. The assumption is that men are less in favor of gun control than are women. Women are more in favor. So in a 2-sample case, Chapter 8 is a 1-sample case. In a 2-sample case, that's Chapter 9, you'd bring down 2 samples. Now, generally what happens in this sort of a circumstance, you bring down 1 sample, but in the drawing down of that sample, you've taken care to make sure that there's an adequate number of men and an adequate number of women in order to be able to have sample size in each one of those categories of gender to be able to distinguish differences between them. So you'd want to have at least 100, let's say, men and 100 women. So that Chapter 9 is really about finding the differences between these two as opposed to the differences in Chapter 8 that are more vertical. These are more horizontal. And it's the same kind of situation that we don't know really what the difference is between male and females on gun control in the population. So we draw down a sample to test the differences within the sample. One of the concepts that's important here is independence. You want to have these men and women, let's say, in these samples, independent of one another. In other words, you don't want spouses or significant others being interviewed. If you knock on a door of a house and a woman answers, you ask her the question. Then if you ask if her husband's home and ask him the question, likely because they are a couple, they're going to have taken on a similar view. So it will make your finding, shall we say, spurious. It's a good word, spurious. What you'll want to do is you'll want to do some assurance to yourself and to your funding agency that you're doing this independently. Maybe in one neighborhood you do men, in another neighborhood you do women, or maybe every other house you do women and every other house you do a man. whatever you would want to do to make sure that you've got some independence. The other thing there that's important is pooled. In this case, what we do is we take the two sample sizes and pool them. So keep that in mind. There are pooled estimates once we start doing the calculation. This is particularly important for t-statistics. Remember, if the t-statistic in Chapter 8 and in Chapter 9, if the sample size is less than 100, then you do the t-statistic. If it is 100 or more, then you do the z. Well, in Chapter 9, if you pool the two and the sum is less than 100, then you would do the t. If you pool the two and it's over 100 or 100 and over, then you move on with the z. And that's true even if, say, one sample is 70 and the other sample is 120. If you add them up, that's 190, so that's pooled, it's over 100, so you go on with the z distribution. I think that's pretty much the logic of hypothesis testing, and some explanations and ideas for answering question 3. So I'm going to close this out and send it up to YouTube and get it converted to a YouTube video, and once it's done I'll send it out to you and turn on the exam 2 hours between now and midnight on Friday. Don't use your text. I'm not saying you can't. I'm just saying don't, because you'll waste your time going through the pages. Use a 5x7 card in front of you. Lay out some things important for you to remember, and then proceed at that point. I don't think I'll do it over the weekend, but first thing Monday morning or sometime on Monday, I'll go into Blackboard and I'll grade those, and then I'll send you individual email. Unless I can post them on Blackboard, I might be able to post them on Blackboard, and then I'll let you know your grades are out there. And somewhere before the end of the day on Monday, I was saying at the beginning that I might do it at the end of the day on Monday, but it might more likely be on Tuesday. I'll send individual emails about your course grade. All right, so thank you very much, and I guess this will be the last time we'll see one another, so thank you for your good work this semester, and wasn't no easy thing, that's for sure, doing statistics online, and I'm proud of the way you did it. You did it well. So hopefully one of these days we'll run into one another, really, either in HEB or in a class. So have a good holiday and hope to see you soon.